So in our last video, I talked about designing an experiment that was a blind or double-blinded experiment and using a placebo for our control group. And I said that one of the reasons that you do this is to eliminate any bias. So a bias is when you sort of make an assumption based on what you already know or what you think should happen. So for example, if you really want your data to support your hypothesis, maybe you're trying to publish a scientific paper and your career is on the line. You really want to support this hypothesis. Well, the data doesn't always show what you want it to show, but you might interpret it in a particular way that makes that data sound good or pushes a particular agenda. So when we are interpreting our results, and it really comes down to experimental design and interpreting our results, we have to watch out for introduction of bias into our experimental design and into our conclusions about those hypotheses. So here's an example. This graph shows the percentage of papers published with a female first author. So this would assume that the researchers felt there was some sort of bias against female scientists. So they looked at the total number of publications from a female scientist, and they found that when the reviewers knew the sex of the author, they were less likely to accept their paper than when the reviewers did not know the sex of the author. So these are the same papers being submitted for publication, but when it was a female author, it was accepted less. There's a bias. Had none of these papers indicated in any way whether the individual was male, female, or otherwise, they would not have known how they were associated, and they could not have made any assumptions based on the sex of the individual. So you want to watch out for things like that. You want to watch out for bringing in outside preconceptions of what you want your data to be or what you think it could be. And I think that this happens a lot, and people do it unintentionally, not necessarily researchers who are employing the scientific method, but when individuals hear something in the news, they immediately attach their bias to it. That's not to say that it's always bad. I'm not saying that it's bad. But what I am saying is you just have to watch out for how your previous ideas, your previous knowledge, your previous feelings are going to affect how you interpret your data. And if we're using the scientific method, we do not want any biases. We want to keep that out of our analysis, because remember, science is supposed to be empirical. It's supposed to be fact-based. And if you start bringing in feelings, you're no longer making it fact-based. One way that we can reduce biases is to use statistics. So statistics is a set of tools that help researchers analyze their data to basically determine if there's a real trend. And the more data you have, the more experimental repeats you have, the bigger your sample size. In other words, the higher number of test subjects, the more likely you are going to be able to observe real trends. And statistics can help you realize if you're seeing those real trends. And they can also help you determine if those trends are significant from one another. So statistics can give you a range of values. Say, most people fall within this range. It can give you a distinction between when two things are different. So over here on the right, we have human height in statistics. So this is telling you the average height of a female. It's telling you that there is a range for the average height. Over here, we've got males. and the average height of males. So the question here would be, is there a difference in height between male or females? Well, statistics can help you determine if this difference, this 5 feet 4 inches or 5 feet 9 inches, is actually enough to be considered different. Statistics can also tell us how much variation between two groups is enough to say that it's different. So we aren't going to talk about any specific statistical tests, but as you are thinking about how you're going to analyze your data, you want to also think about how you can use statistics, because those statistics are going to make your data even more powerful. So here we've got an example that says students without textbooks score on exam. They score 60% plus or minus 5%. So the average range without using textbooks is between 55 to 65% on the test. When students use the textbooks, they range from 90 to 100% on the test. So statistics is going to tell you, are these values different? Are they different enough to say, yes, textbooks make a difference? This is all hypothetical. I'm going to say it's true, though. You should use your textbook. You should be reading your textbook. All right, so statistics can also help us identify relationships between variables. They can also tell us when no relationship exists. So a positive correlation means that one variable affects the other in a way that if one increases, the other decreases. But it is important to remember that correlation is not causation. So correlating means that two things happen at the same time. Causation means that one thing happening causes the other to happen, and they're not the same thing. So statistics can help us identify the difference between correlation and causation. So sometimes people think they're doing science, or they just want people to think they're doing science. And that can cause some trouble, especially in advertising. So have you ever looked at something that has some sort of claim on it and you thought, oh, that's really healthy, I should buy that? Did you look at the actual study? Did you look to see whether or not they were actually doing a scientific experiment? So pseudoscience is when individuals make claims that sound scientific, but aren't actually backed up by any trustworthy scientific studies. So these might be vague claims like 4 out of 5 dentists recommend, or essential nutrients, things like that, that make you think that they are good or healthy and whatnot, when actually they might not be. We also need to watch out for anecdotal observations. These are where one or a few people make conclusions and decide that there's a link between them when there may not be, or somebody makes a claim based on their experience. This is often in the form of a superstition. So an apple a day keeps the doctor away. Do apples really make you that healthy? I don't know. So you want to watch out for anecdotal observations as well. So when people don't do science correctly, it can lead to dangerous outcomes. So one of the big ones was the claim a few years ago that vaccines cause autism. Well, it turned out that the study that claim was based on actually had a whole bunch of fake evidence, and it was filled with biases. But that has caused a huge vaccine scare that we basically can't get rid of. So when we had sort of biases and anecdotal evidence in this study, it caused a big healthcare scare, and it's caused a lot of people to not become vaccinated. Now, there are other reasons that people might not be vaccinated, and that's a different story, but the point here is that if you are trying to do science correctly, you need to keep out anecdotes and biases. So I like this little picture here. It says, always base opinions on anecdotal evidence, because the story your brother told about his neighbor who had a coworker that knew someone. Basically, this is saying, don't listen to people's stories. Look at the fact-based science. So just to sort of recap that, there is no link between vaccines and autism. Based on international scientific community review, in subsequent studies and subsequent review of literature, no link was found. But it appears that there is a link. So why does it appear that more autism cases why is autism more prevalent now than ever before? Oops, sorry about that. One of the thoughts is basically timing. So the round of vaccines is given around the time that autism begins to show itself. So here we have a correlation, but not necessarily causation. Another thing is just greater awareness. So why are there more cases of autism now? Well, because more people are studying. It's more prevalent in the sense that we know more about it, and it is something that we have labeled with a specific set of symptoms. And so now that we have a name for some of those symptoms, it might appear that autism is more prevalent. So to sum things up, there is a limit to what science can do. So the scientific method needs to remain fact-based. So you can't evaluate anything that is not empirical, that is not data-driven. So belief systems, value judgments, and subjective information all fall outside of the realm of science. Basically, faith issues and supernatural issues. You cannot design an experiment to answer these questions. Science can't give moral statements or give insight to ethical problems. So science can generate data, but it can't tell you right or wrong. And then this last note here, technology is not science. Technology is the use of science. So we have an example over here of this sophisticated prosthetic arm. That is an application of science based on an understanding of mechanics, and both the mechanics of the machine and the mechanics of the arm.